What does a simple falling apple have in common with the cosmic dance of planets around the sun? This question, seemingly simple at first glance, sparked a revolution in our understanding of the universe and led us to one of the most profound discoveries in the history of science. The answer lies in a fundamental force that binds our entire cosmos together. Picture a universe where everything is interconnected by invisible strings. A realm where each object, from the tiniest speck of dust to the largest galaxy, silently whispers to every other body in the cosmos. This is not science fiction. This is the reality we live in, governed by the most fundamental force in the universe: universal gravitation. Every single moment, this force orchestrates an intricate ballet of celestial bodies, from the graceful orbit of our moon to the majestic spiral dance of entire galaxies. Throughout human history, we've gazed at the stars, wondering about our place in this vast cosmic theater. Why doesn't the moon simply fall to Earth? How do planets know their precise paths around the sun? These questions haunted philosophers and scientists for millennia. Today, we understand that these cosmic movements follow the same rules that guide an apple falling from a tree, a profound realization that changed our perspective of the universe forever. If you've ever pondered these cosmic mysteries, if you've ever looked up at the night sky and wondered about the invisible force that keeps everything in perfect harmony, then join us on an extraordinary journey through the deepest mysteries of the cosmos. Together, we'll unravel the elegant simplicity behind the most powerful force in existence, a force that speaks the universal language of attraction across the infinite expanse of space and time. In the 17th century, the story of universal gravitation began with a moment that would forever change our understanding of the cosmos. A young Isaac Newton, resting in his family garden at Woolsthorpe Manor during the Great Plague of 1665-1666, observed an apple falling from a tree. This simple event sparked a chain of thoughts that would revolutionize physics and our view of the universe. Unlike countless others who had witnessed falling objects throughout history, Newton's brilliant mind approached this commonplace occurrence with unprecedented insight. He pondered why objects always fell straight toward Earth's center, and more importantly, he made a remarkable intellectual leap. He wondered if this same force that pulled the apple downward might extend far beyond our planet's surface, reaching all the way to the moon. This connection between terrestrial and celestial phenomena was groundbreaking. Before Newton, scientists and philosophers had long believed that the laws governing heavenly bodies were entirely different from those on Earth. Aristotelian physics, which had dominated scientific thought for nearly 2 millennia, maintained that the celestial realm operated under perfect circular motions, while earthly objects followed different rules entirely. Newton's revolutionary hypothesis suggested something far more elegant, a single, universal force that governed both the falling apple and the moon's orbit. He reasoned that if this force existed, it must diminish with distance according to a mathematical relationship. Through meticulous calculations, he determined that this force decreased with the square of the distance between objects. This work did not happen overnight. Newton spent nearly 2 decades developing and refining his ideas before publishing them in his masterwork, Principia Mathematica, in 1687. His mathematical description of gravity not only explained the moon's orbit, but also provided a framework that could predict the motions of all celestial bodies with unprecedented accuracy. The apple story, while often simplified in popular retellings, represents a pivotal moment in scientific history, the recognition that the same natural laws govern both earthly and celestial phenomena. This unification of terrestrial and celestial physics marked the beginning of modern physical science and demonstrated that the universe operates according to consistent, mathematically describable laws. What makes this historical moment particularly remarkable is that Newton didn't just identify the force of gravity, He provided a comprehensive mathematical framework that could precisely describe and predict gravitational effects. His work explained everything from the trajectories of cannonballs to the orbits of planets, from ocean tides to the paths of comets, all using the same fundamental principles. The universal law of gravitation stands as one of the most elegant and powerful principles in physics, describing a fundamental force that shapes our entire universe. This remarkable law, expressed through a precise mathematical equation, reveals that gravity is not just a force on Earth, but a universal attraction between all matter in existence. At its core, Newton's law tells us that every single particle of matter in the universe attracts every other particle with a force that we call gravity. This means that right now, your body is not only being pulled by the Earth, but is also experiencing tiny gravitational pulls from everything around you, from the buildings in your city to the distant stars in our galaxy. The mathematical relationship demonstrates that gravitational force depends on two crucial factors: mass and distance. The greater the mass of the objects involved, the stronger their gravitational pull becomes. This relationship is directly proportional, meaning that if you double the mass of an object, you double its gravitational force. This explains why massive celestial bodies like the Sun have such powerful gravitational fields. However, distance plays an even more dramatic role in this cosmic dance. The gravitational force decreases with the square of the distance between objects, following what we call an inverse square law. This creates some fascinating real-world implications. For instance, when you double the distance between two objects, the gravitational force doesn't just halve, it decreases to 1/4 of its original strength. Triple the distance, and the force drops to 1/9. To put this into perspective, imagine two people standing 1 meter apart. The gravitational attraction between them, while incredibly small, is measurable. Now, if they move to 2 meters apart, the gravitational force between them becomes 4 times weaker. At 3 meters, it becomes 9 times weaker. This exponential decrease explains why we only notice gravity's effects from very massive objects like planets and stars. The force becomes vanishingly small over large distances. The Sun provides a spectacular example of gravitational force in action. Its immense mass, approximately 333,000 times that of Earth, creates such a powerful gravitational field that it can keep multiple planets, dwarf planets, asteroids, and comets in orbit at distances of millions of kilometers. This same force prevents our entire solar system from flying apart, maintaining a delicate balance between gravitational pull and the orbital motion of celestial bodies. The precision of this law is remarkable. Using Newton's gravitational equation, scientists can calculate the exact force between any two objects in the universe, provided we know their masses and the distance between them. This predictive power has allowed us to plot spacecraft trajectories, discover new planets, and understand the structure of galaxies. It's worth noting that while Newton's law works perfectly for most practical purposes, Einstein's general theory of relativity later revealed that gravity is actually a curvature in space-time caused by massive objects. However, for most calculations outside of extreme conditions, like black holes or precise satellite navigation, Newton's formulation remains remarkably accurate and continues to be used by scientists and engineers worldwide. Gravity's practical applications permeate every aspect of our daily lives, extending far beyond the simple act of keeping our feet on the ground. Let's explore how this fundamental force shapes our world in ways you might never have imagined. One of the most visible manifestations of gravity occurs in our oceans through tides. The gravitational interplay between Earth, Moon, and Sun orchestrates a daily ballet of rising and falling waters. The Moon's gravitational pull creates bulges in Earth's oceans, causing high tides on both the near and far sides of our planet. This tidal force not only influences marine ecosystems and coastal environments, but also generates renewable tidal energy, which some countries harness for power generation. In the realm of space technology, gravity plays a crucial role in satellite operations. Every satellite orbiting Earth exists in a perfect balance between gravitational pull and its forward momentum. This understanding has enabled us to position thousands of satellites that serve various purposes, from weather forecasting to telecommunications. Engineers must precisely calculate gravitational effects to maintain these orbital paths, considering not just Earth's gravity, but also the subtle influences of the Moon, Sun, and even the slight variations in Earth's gravitational field. Perhaps one of gravity's most remarkable applications lies in your pocket, your smartphone's GPS system. GPS satellites must account for both special and general relativity effects caused by gravity, as time actually flows slightly differently at orbital altitudes compared to Earth's surface. Without these gravitational corrections, GPS systems would drift by about 11 kilometers per day, making accurate navigation impossible. The formation and structure of galaxies showcase gravity's influence on a cosmic scale. Gravity binds billions of stars together, shapes spiral arms, and even determines how galaxies interact with each other. Understanding these gravitational dynamics helps astronomers predict galaxy collisions and study the distribution of dark matter in the universe. Gravity's applications extend into numerous other fields. In construction, architects and engineers must account for gravitational loads when designing buildings and bridges. In medicine, physicians study how reduced gravity affects human physiology, crucial for long-term space missions. Even in agriculture, plants' response to gravity, known as gravitropism, influences how they grow and develop. Now, turning to our solar system's gravitational hierarchy, here's an intriguing question to ponder. After the Sun, which object in our solar system exerts the strongest gravitational pull? While many might immediately think of Jupiter, the largest planet, it's worth considering factors like density and mass. Jupiter's enormous size and mass indeed make it the gravitational heavyweight among planets, with a mass 2.5 times that of all other planets combined. But could there be any surprising contenders? Think about the relationship between mass, density, and gravitational force, and consider how these factors might influence your answer. This question isn't just academic. Understanding the gravitational influences of different celestial bodies helps us plan spacecraft trajectories, predict orbital perturbations, and even study potential asteroid impacts. What's your thought on this cosmic question? Share your answer and reasoning in the comments below, and let's explore this fascinating aspect of our solar system together. Get ready to have your mind blown by some of the most fascinating aspects of gravity that challenge our everyday understanding of the universe. These incredible phenomena demonstrate just how extraordinary and complex gravitational forces can be. Let's start with one of the most mind-bending objects in the universe, black holes. These cosmic behemoths represent gravity at its most extreme. Imagine a force so incredibly powerful that it can trap light itself, the fastest thing in the universe, traveling at 299,792,488 meters per second. When a massive star dies in a supernova explosion, its core can collapse into a point of infinite density called a singularity. Around this singularity, gravity becomes so intense that it creates a boundary called the event horizon, beyond which nothing, not even light, can escape. This is why we call them black holes. They are literally invisible because they prevent any light from reaching our eyes. The gravitational force at the event horizon is so strong that time itself begins to warp and slow down, an effect predicted by Einstein's theory of relativity. Now let's debunk a common misconception about astronauts in space. Many people believe astronauts float because there's no gravity in space, but this isn't accurate at all. At the International Space Station's orbital height of approximately 400 kilometers, Earth's gravity is still about 90% as strong as it is on the surface. The sensation of weightlessness occurs because both the astronauts and their spacecraft are in a constant state of free fall around Earth. They're falling toward Earth at the same rate that Earth's surface curves away from them, creating a perfect orbital trajectory. It's like being in an elevator where the cable has been cut, except this fall continues indefinitely. This state of perpetual free fall allows for unique scientific experiments and has profound effects on the human body, from muscle atrophy to changes in blood flow patterns. Here's another fascinating fact that challenges our perception of our own planet. Earth isn't actually spherical. Instead, it's an oblate spheroid, meaning it's slightly squashed at the poles and bulged at the equator. This shape is the result of two competing forces: gravity, which tries to pull everything toward the center, and centrifugal force from Earth's rotation, which creates a bulging effect around the equator. The difference is significant. Earth's diameter at the equator is about 43 kilometers greater than at the poles. This bulging also affects Earth's gravity field, making gravitational pull slightly stronger at the poles than at the equator. This variation in gravitational strength across Earth's surface is so precise that geologists can use gravity measurements to detect underground mineral deposits or predict volcanic activity. But wait, there's more. Did you know that gravity also bends light? Einstein's theory of general relativity predicted that massive objects could bend light rays, an effect called gravitational lensing. This prediction was first confirmed during a solar eclipse in 1919, when scientists observed stars appearing to be in different positions because their light was bent by the sun's gravitational field. Today, astronomers use this effect as a cosmic telescope, studying distant galaxies and even searching for exoplanets by observing how light bends around massive objects in space. Even time itself is not immune to gravity's influence. Time actually passes more slowly in stronger gravitational fields, an effect called gravitational time dilation. This isn't just theoretical, it's so real that GPS satellites must be programmed to account for the fact that time passes slightly faster in orbit than on Earth's surface. Without these corrections, your navigation apps would quickly become inaccurate. These mind-bending facts reveal that gravity, while seemingly simple in our daily experience, harbors profound complexities that continue to challenge our understanding of the universe. From warping space and time to shaping our planet and enabling space exploration, gravity proves to be one of the most fascinating forces in nature, full of surprises and continuing to inspire new questions in modern physics. Universal gravitation reveals a profound truth about the nature of our cosmos that borders on the philosophical. We exist in an intrinsically interconnected universe where nothing is truly isolated. This fundamental principle challenges our perception of separation and individuality in the most beautiful way imaginable. Consider this extraordinary thought. At this very moment, every single atom in your body is engaged in a cosmic dance of attraction with every other piece of matter in the universe. The calcium in your bones maintains a gravitational dialogue with the stars of the Andromeda galaxy. The iron in your blood shares a gravitational connection with the supermassive black hole at our galaxy's center. While these forces may be infinitesimally small, they are real, measurable, and eternal. This interconnectedness speaks to something deeper than mere physics. It suggests a fundamental unity in nature that transcends our everyday experience. We often think of ourselves as separate entities, distinct from the world around us, but gravity tells a different story. It whispers of a universe where boundaries are more fluid than we imagine, where the distinction between here and there becomes increasingly meaningless as we zoom out to the cosmic scale. The universality of gravity also highlights our place in the cosmic web. Every breath you take slightly alters the gravitational field of the entire universe. Every movement you make sends gravitational waves rippling through the fabric of space-time, traveling at the speed of light to the farthest reaches of the cosmos. While these effects are incredibly subtle, they remind us that we are not merely observers of the universe, we are active participants in its ongoing evolution. This perspective transforms our understanding of our cosmic heritage. The atoms in your body were forged in the hearts of dying stars, scattered across space by gravitational forces, and eventually gathered together by the same force to form our planet, and ultimately, you. Gravity not only connects us to the present universe, but also links us to its history and future. The implications of this interconnectedness extend beyond physics into questions of environmental stewardship, social responsibility, and our collective future as a species. If everything is connected, then our actions have consequences that ripple far beyond our immediate surroundings, both in space and time. As we conclude this exploration of universal gravitation, we stand at the threshold of an even more profound understanding. Einstein's general theory of relativity would later reveal that what we experience as gravitational force is actually the curvature of space-time itself. This revolutionary insight would transform our understanding of gravity from a mysterious action at a distance into a fundamental property of space and time themselves. In our next episode, we'll delve into Einstein's groundbreaking work on general relativity, which completely revolutionized our understanding of gravity. We'll explore how he reimagined gravity not as a force, but as the very shape of space-time, leading to predictions of phenomena like gravitational waves, which were finally detected in 2015, proving Einstein right once again. If this journey through the unifying force of gravity has sparked a sense of wonder in you, if it has made you feel more connected to the cosmic dance that surrounds us, share this video with someone who needs to experience this perspective. Share it with those who might benefit from understanding their place in this interconnected cosmos. Sometimes, the most profound changes in our lives begin with a shift in perspective, with the realization that we are all part of something vastly larger than ourselves. Remember, every time you look up at the night sky, you're not just observing distant points of light. You're actively participating in a gravitational relationship with those celestial bodies. You are, and always have been, an integral part of the cosmic web that binds our universe together.